Good evening, everyone. Can someone confirm if I'm audible and the screen is visible? You could use the chat window as well, in case you are able to hear me. Okay, I'm not sure if there is some issue. Am I audible? Okay, let's see. So, welcome to the week 3 session for clearing the doubts. Um, can you tell me if your week 1 and week 2 assignments were good? Did you get the scores for that? And in case you have any doubts in those assignments, please let me know so that we can solve those questions and then we can move ahead to week 3. Okay, so since there are no doubts, I'll move ahead. Um, but in case you have any doubts in the meanwhile, please feel free to use the chat window. I'll be, anyways, monitoring that. So, yes, so in the week 3, the topics that have been covered is on real-time task scheduling for cyber physical system. So until now, for week 1, we had taken a look at some of the motivational examples and some of the compute platforms that are being used in cyber physical system. In the last session, we went over this real-time sensing and communication for cyber physical system. And this time we are actually going to understand how this task scheduling actually works. Like if you have multiple tasks, but if you have some limited resources, then how are you going to schedule your task? Or if you have multiple tasks and you want all of the tasks to be successful, then how do you actually schedule them properly based on their processing time, based on their period, and based on their deadlines as such, so that every task gets computed before their deadline. Okay, so this is the basic idea about real time task scheduling. And by real time, you should understand that we are talking in terms of millisecond, because the response time has to be as less as possible. So let's get started with this. So this is the outline. We have different topics within this. So the first one is overview, and then we have this processor level task scheduling. Then it is processor level WCRT analysis, then bus level scheduling, and then CAN bus level WCRT analysis. So in general, right now I'll just walk through these some of these concepts just for revision, and then later we will go back to the assignment questions, and we can discuss some of the hints and um, like suggestions on how to approach those questions and how it is going to help in your assignments. Okay, so in the first section, in general, the introduction of this distributed embedded CPS is this. So these are compute units. So if you have one of the compute unit, let's say, okay, and there are how many? Four such compute units. So we have CU3 and we have CU4 also. So eventually you have, let's say, a total of four compute units. So how do you actually communicate between these, and how do you actually interact the like the data transfer between these compute units such that you get the real-time application going? Okay, so over here, one important aspect is that we have a communication bus. All right. And then now over here, when this is your physical plant, there are a few things to take care of. One is this TC, which is the control task. Then we have TA, which is the actuation task. And then we have this TTX, which is transmission task, and TRX, that is the reception task. Okay. So basically, there are these two things that are important, which is transmission and reception task. And then control task, actuation task, and sensing task are more to which are over there in the compute units. But these two are the actual ones that actually get into the communication bus, and then the other compute units um, take those. All right. So now let's say if you have a physical plant, so there has to be a sensor, right? And the sensor is going to send some of the data to your compute units. So if this is your TS, which is basically sensing task, now on the sensing task, you are going to do some kind of computation, and then you are going to generate some kind of a control, right? So once you have generated this control task, that in turn converts into something which has to be transmitted back to some other compute unit that is actually actuating to some of the units to make sure that your sensor value remains what is desired, right? Because in your control systems, what do we have? We have something called as a set point. By set point, you mean, let's say, if you have a temperature sensor, and let's say if you want to set it as 50 degrees Celsius, 50 degrees should be the room temperature, let's say. And then if it is current one is 60 degrees Celsius, then you get the error of 10 degrees Celsius, and the control commands that you generate are dependent on the error that you are getting. Okay, so that's what is the thing. And then once that command gets scheduled onto this communication bus, and later over here this other compute unit has to receive the same command, right? So the scheduling of these different tasks on the communication bus is actually what we are going to go into in this session. There are different kinds of scheduling depending on the different kinds of tasks we have, and different kinds of priorities, deadlines, all those things that we have. Okay, and once this message has been passed on to in the bus, then what happens? This one receives it as a TRX, because you would see, right, this TTX is actually going here, and from the same bus unit it is going to the other compute unit, and then that feeds into your actuation task, and that goes back to your physical plant. Okay, so this is how the entire thing works in general. So over here, the basic requirements of the CPS compute platforms is that you have to do the signal processing first, which means that you have to filter out the plant state data. You have to do some kind of state estimation, right? Then you have this onboard intelligence that can run several optimizations for real time processing, problem solving. This is what we are going to check today. All right. Then we have this low power consumption. So when you have this cyber physical system, you need to ensure that your systems do not take up a lot of power, right? Because if those itself are taking power, then what will the actual units do? Like what will the power plant do? Right? So this is typically performed with help from onboard batteries, like let's say Raspberry Pi, that takes in very less power, right? And even if you have these NVIDIA Jetson devices that I talked about in the last sessions, they have a GPU on board. But even though some of these devices like Jetson Nano, they can operate on 5 watt, which is very less. And then if you have Jetson Orin Nano, they operate on like 15 watts or so. So they are very low power computation devices. And then we need to use these low power processors instead of workstation class processor. Okay, so we need to use these microcontrollers and all of that. All right, so in a compute unit of this embedded CPS, we have these different types of task as we talked about. So we have a host controller, we have the communication controller, we have this communication bus drivers, and then you have this entire communication bus. This will go into detail later, but take a look at this one. You have this as the sensing task. Okay, once that sensing task is generated, you have the control task based on that, and then that becomes your transmission task, the task that needs to be transmitted, and that goes to your bus. Okay, and this is like, let's say, one of the periods. So this entire cycle keeps happening after every period of that compute unit. Okay, so there are two different kinds of task. One is application task, which is in the host microcontroller, and the communication task, which are in the communication controller and the bus drivers. Okay, so application based tasks are only the sensing and control task, and maybe the actuator will come into picture later. And in communication task, you have only these two. Okay, so this is similar. These are fine. This is what we have um, gone through, but this is more of an example. Okay, so let's see. Over here, after we understood these different kinds of tasks that we have sensing, then you got control task, you got actuation task, then you had the transmission and the receiving task. Okay, so all those kind of tasks, we want to schedule them such that they execute within their deadline. And why are we talking a lot about deadlines? Because we are talking about these real time scheduling. Okay, so every task which is critical in nature, because we are dealing with real time, it becomes very important that you execute it within the deadline, because if some task gets executed after the deadline, you cannot use their output and the task becomes stale. Okay, now if let's say you have multiple tasks, so if you have only one task and that maps to only one processing element, let's say whatever your processor or ASIC or whatever it is, there is no need of an operating system. But if you have these multiple tasks that are mapped to only one processor, that's when the actual work starts. Okay, so you need to have some kind of a bare bones scheduler, or you can provide an operating system that actually interfaces among low level drivers and high level tasks. Okay, so somehow, so this scheduling and all of that happens only when you have one processor, or maybe like multiple processor but multiple tasks. It can never happen if you have only one task and one processor. Okay, because that time scheduling just doesn't come into picture. All right, so now the major requirements are that you have to map, you have to order, and you have to time them. All right, so mapping means which task gets mapped to which processor. So in case you have multiple processors, you have multiple tasks, which ones get processed on which ones. So this also comes as a part of your operating systems course. Ordering is in which order will each processor execute tasks assigned to itself. So let's say you have processor 1, 2, and 3. This has task 1, 2, 3. 4, 5, and this is 7. So over here, since this processor has only one task, this is fine. In this processor, you need to check that will tau 4 get first or will task 5 get first executed, and similarly for the processor 1. Now, once you have decided in which order they are going to be executed, we need to decide at what time they are going to be executed also. Okay, so if let's say this starts at 0 milliseconds and this starts at 10 milliseconds, okay, but now if you have checked their starting time, you need to also ensure that while you are doing all of that, the um, resulting schedule, so schedule means that the tasks that are assigned to a process, you have the order of those tasks that are going to go into the processor, and you need to know the details at what time they are going to be executed. So that's like a schedule, like we have our daily schedule, right? We know at what time what things we are going to do. So similar to that, every processor has a schedule, which means that at what time they are going to execute which task. But you need to ensure that that schedule is feasible, which means that let's say if a task, if let's say this takes like 10 milliseconds to run, this takes 1 millisecond to run, the deadline for this is 11 milliseconds. Okay, for now let's say this takes 5 milliseconds, and for this it is how much, let's say 10 milliseconds is the deadline, and 10 plus 5, let's say for this it is 16 milliseconds is the deadline. Okay, so now if we schedule tau 4 first, it will take the entire 10 millisecond, right? And then the task 5 will get executed, which means the task 5 will get completed at the end of 15 milliseconds. But the deadline of task 5 is already violated. So that's not a feasible schedule. So what we do is, let's say we schedule task 5 first. It took 5 milliseconds, it is within the deadline. Okay. And then you started task 4, which started at 6 milliseconds. It took 10 milliseconds and it ended at 16. So both the deadlines are satisfied in this case. So in that case, the schedule of your P2 would be task 5 and then task 4. Is this example good?
Yes.
Okay. So now, if all the decisions that you take are during the design time, your scheduler is supposed to be fully static or offline, right? Because you know all this information and you have scheduled already based on the processing time and based on the deadline. Now, if all the decisions are at runtime, that's called as a fully dynamic scheduler. So instead of this, let's say this processing time you kind of get exactly during the runtime. You do not have any information about this before you actually schedule the task. Okay, so that is a fully dynamic scheduler. And then you can either allow or disallow task preemption before completion. So can anybody tell me what preemption means?
We have to stop in between and then wait for the another turn time.
Mhm. Correct. So you stop one
Suppose
task, you preempt some other task, and then you schedule this task after that, right?
as per the priority, suppose some job has a more priority than the present task, so we have to stop that present task, then execute the more priority task, then again we have to resume.
Correct. Okay, good. So that's what we do those things, okay, in terms of scheduling. So now there are different kinds of task model itself. Okay. So we have this scheduler may or may not support any arrival of task. Okay. Then the task models may be periodic, which means that they need to be executed or they arrive once every t time units, and t is called as the period of that task. Okay. So this is actually being used in a lot of your numericals from this assignment. Then we have this aperiodic, which means there is no such time period or so on. The sporadic is like t has a lower bound and then you have some kind of constraints. Now, this is basically like a life cycle of a task. So once you have this This is basically the time axis. And then you have the release time, which means that at this particular time, your task was created. And then your task execution started. Let's say over here, some kind of preemption occurred. Then this was the time when other task was getting executed. And then you resumed your task. Then you finished your task. So basically, this plus this is going to be your execution time of this particular task. And let's say if this is the deadline, so since you have finished way before the deadline, your task is successful. And from the release time until the finish time, this entire time is called as the response time. Okay. So yeah, this is basically the overall life cycle. You have execution time, release time, finish time, and response time. So there are a few questions based on these, and yeah, we'll go through that one by one. So now over here, there are different kinds of scheduling also. We have hard real-time deadlines or soft real times, which means a hard deadline is like you need to execute your task within a certain deadline. Soft deadlines means that even if you overflow your deadline by a little bit, that's okay. There are certain mechanisms by which those tasks can be handled. Then you have non-preemptive or preemptive or fixed and dynamic priority. And a priority can be different than a deadline, or it can change or remain constant during task executions. Okay, so what is the algorithm, scheduling algorithm, for which the priority is a deadline? Can somebody just take a guess?
Early deadline first.
Correct. It's called as earliest deadline first. Okay, so let's see. Um, we'll go through some of these, and I'll also work through some of the examples that is going to help you with the assignment questions.
Ma'am,
So the
this
first
this
one is
week assignment
yes.
is very, ma'am, this week assignment is very tough. Please help us.
Sure, sure. I'll do. By the way, I think you joined a bit late. So before I actually start this
Ma'am,
scheduling part,
I will tell you the
how
one
was
one
week one and
problem in
week
the
two
link.
assignment?
Ma'am, excuse me. Ma'am, I was trying to join, but what link you have given, it
Mm-hmm.
is not. I am not able to penetrate in your network. So I request you to give ID also, that meeting ID also, because of security reason of your what you say, in-house security. I cannot join
Mm,
via my this Android tablet. So
okay.
I have linked. I have gone through the SWAM portal. Then I have
Uh-huh.
able to do that. Otherwise, from team also I can go na. But I, because of the link ID is not available, so I have to. That's why 10 minutes is wasted.
I couldn't understand your problem. Could you tell again? So you have the
Ma'am,
Teams link
you have given one
on the
link
Swam
which
portal.
we,
Yes.
yes, and you have given a link in a mail from which we have to click and we will go, okay, to the to
Correct.
this meeting. But
Right.
because of security reasons today it is not allowing. So what I have gone, then I have gone log into the SWAM portal. Then from that announcement I came.
Right.
So now they are asking the ID, that link ID, na, that meeting ID, which was not there in that link.
Hmm. Did others also face the same problem?
I don't know. Now I learned today the lesson. I will go via SWAM portal only.
Okay, so if you click from the Swam portal, you are able to join, right?
Yes, yes. So that's why my 10 minutes is waste. So this
Okay,
every day
okay,
is
okay.
learning, and this I learned today.
Okay, fine, fine. So I think you should be fine with the team link. It shouldn't be a problem. Yeah, one thing I was asking. So, how was week one and week two assignment for you? I believe the assignments
I
closed
got
and you
70
already have
70
your.
marks. I got 70 marks in both, but one of the obvious error, like that I joined adjoint, sorry, that inverse adjoint, that was confused. So
Okay.
small errors. But now I believe that they will give us what that solved examples also. Then we will match.
Okay, so do you have any doubts? Because now, while when I will start this scheduling problem, I will actually do it
Ma'am,
in parallel, like solve
I
the
request
assignment and
you.
come
I
back to
don't
the
know about
theory part.
others. Whatever is
Hmm.
gone is the past. Now we have to concentrate on third, because third assignment is very tough.
Yeah, yeah, that is fine. That is one thing. But I just
First,
because we
our
have time, so
third. First, we
I
will do
wanted.
third one. Then we will go first and second one. If you please start with first the third assignment.
No, actually, the course, the like our session goes like that, right? We initially discuss the questions from the previous one, and then we dive into the next ones, right? So if you have any questions from the earlier week assignment, please ask now. Otherwise, we can just continue with the third week. It's fine.
But that solution release is still we have to wait now, because they will give the solution. Then we will match.
Oh, you haven't gotten the solution yet.
Yes, yes, yes. So that is why I said ki we will wait
Okay,
for.
got it. All right, that's fine then. Okay, so anyways, let's start with week 3. So from here, actually, it's majorly the scheduling part, but we will check each question and we'll try to find some of the alternative theory also for that. Okay, so one question which is based on this rate monotonic scheduling. So let's start with this. So rate monotonic scheduling is this RMS. So we have a set of tasks which is tau 1, tau 2 up till tau n. Okay. So task tau I with a release time of Ri, period of Pi, and deadline of Ri plus JPI for the ith execution. So I hope release time, period, and deadlines are clear for all of you. So now
Yes.
what do we do is there are two cases. You have this tau 1 and tau 2. So now since this is the P2 is the period of tau 2 and P1 is the period of tau 1, E1 is the execution and E2 is the execution for tau 2. Now let's say this from over here, the next P2 starts. Okay. So in this kind of a scenario where this is your execution time and this is your execution time for task 1 and 2, preemptive scheduling is resulting in a feasible schedule. And if you don't do preemption, there is no feasible schedule. Why? Because over here, if we execute this one first, then in that case, what happens is, yeah, one more thing over here is that we give higher priority to tasks that have lower periods, which means that the tasks that have a higher frequency, they get the higher priority. Okay. So over here, since the frequency of tau 1 is greater, this one gets the priority. So when this one actually executes, um, yeah, actually, this is what the preemptive schedule is. So when this one actually executes first, okay, the second task stops, and then you have this where this time where you don't have any other task, and your task 2 gets executed, and then once task 1 comes again, then it gets preempted, and then so on and so forth. Okay, so this happens entirely for this time period P2. So now over here, the parts where tau 2 was getting executed is your execution time of task 2. All right. And wherever this dots are seen, that is actually your preempted for task 1. All right. So if you give a preemptive schedule where priority is given to task 2, the schedule is not going to be feasible because if this one gets executed first, then this, and I mean the tasks, actually They violate their own deadline, right? Because at this point the other task will come and all of them will get queued up, and because deadline is not being shown over here, but then the deadline will also start getting violated. All right.
But it all
So
it also violated, ma'am. It also violated the condition what you said. Ki higher frequency will take the priority.
exactly, so that's why this kind of a schedule is feasible, and if you do give priority to tau 2, that is not going to be feasible. Okay, this is again like similar kind of example. Now, rate monotonic schedule, all of these are fine. Yeah, this one is important. So, given a preemptive fixed priority scheduler and a finite set of repeating tasks, let's say you have this with associated periods P1 to Pn, and there is no precedence constraint, which means there is no task dependency. So, if any priority assignment yields a feasible schedule, then the rate monotonic priority assignment yields a feasible schedule. That is fine. So, there is this term called utilization, which is equal to the summation of all tasks, okay, for this particular value. So ei is your execution and p is your period. So execution by period, you sum over all of it, and then you get something called as a utilization, and that utilization has to be less than equal to n into 2 to the power 1 by n minus 1. If this is the case, then your then your schedule is a rate monotonic scheduling is possible, otherwise it is not possible. Okay, so there are certain things how you can get a better utilization, and one of them is this, like either you work through this earliest due date, which is also called as um, whatever is having the lowest execution time, you execute that one first. Okay, so these are more of the proofs, you can go through it. And the other one, since this EDD is not very optimal, you have this earliest deadline first, and all of you know that earliest deadline first is actually something that minimizes your maximum lateness. So it tries to maximize the tasks that complete within your deadline. Okay. And again, so over here they have shown this example, right? So the question says, are the following tasks with given specifications RM schedulable? Okay, so how do you check that RM schedulable? You have to check that condition that your utilization has to be less than equal to that number. So what was the summation for? Was EI by PI. So your utilization was what? Summation of EI divided by PI. I is equal to 1 to n. Okay, so it is 1 by 4 plus 2 by 6 plus 3 by 8. Okay, so you get this 23 by 24, and then you have this number. All right, and then what should it be less than? It should be less than n into 2 to the power 1 by n minus 1. But since over here it is greater than this, so it may not be schedulable. Okay, so that's what was there, and then in the session it was being checked, so that is fine. um but these are okay. Yeah, so another thing is you have this EDF with precedences. Okay, so in case there are some schedules for which deadlines are given, but you have these precedence, which means that a task is dependent on the output of another task. Okay, so where you have a task graph kind of a structure. So the major thing it does is it adjusts the deadline of all the tasks. Okay, and over here, how do you adjust the deadline? You take this formula. Okay, so over here I'll just give you an example. Whenever this kind of a precedence graph is given, for the leaf nodes you don't do anything to the deadlines, but what do? You check the previous ones. Now for 2, what do? If we have to change the deadline for 2, so the deadline for 2 changed one is equal to minimum of deadline of 2, comma minimum of dj minus ej. So deadline of 4 is 3 minus what is the execution time? It's 1 for all of them. Okay, comma. You have to take the minimum of deadline of 5 is 5 minus 1. Okay. Yeah, so basically you'll take the minimum of D2 is what? 5, comma, minimum of 2, comma, 4. So what is it going to be? 2. So you can revise the deadline of this to 2. All right. So this is how things work. And you keep on modifying. So you keep going back and you keep checking that on which ones are the tasks dependent. And then you check the you change the deadline of the previous task. Okay, so that's how it works. So we'll solve
Ma'am,
some of
please,
the
please,
questions.
ma'am, excuse me. Ma'am,
Could
this
you
precedence,
like ask, I mean, could you just
ma'am,
put in the chat window sometimes or raise your hand because interrupting is not good.
sorry, ma'am, sorry. Last
Okay,
time, ma'am, next time I
okay,
will
sure,
keep. Ma'am,
sure.
this precedence graph you will provide us, or we have to know how to draw it?
So for any question, I think they would be providing you. So let's say this last question is involving a precedence graph, right? And they have given you the graph. So for any question that is asking you something based on this graph, it will give you the graph, or even if they don't, you should be able to construct it. All right, because they'll give you the relations among the tasks. Is that okay?
Thank you, ma'am.
All right, so based on these theories, let's see which questions come into that category. So very likely it starts from here. So question number 7, let's start with this. So the question says that construct the schedule according to the preemptive RM policy for the following set of periodic tasks 1, 2, and 3. We have these. Here, CI and TI are the execution time. This is the exec time. This is the period of task, respectively. Okay. And this Tij denotes the jth instance of task I. So over here, the superscript j is actually showing which instance. So in one single time period, there will be multiple instances of the same task, right? A particular instance of a task might appear twice in case there is a preemption. All right. So what is the question? Okay, the question is to construct the schedule, right? So let's see how this works. Um, so I'll help you construct this. So let's say if this is your time, all right, and then you have what? This is 0, let's say 2, 4, 6, 8. All right. And now you have to take this scale which is equal to actually this. So you take the time periods. Okay. So what is your hyper period? So first of all, you calculate this. Your hyper period is actually equal to the LCM of 4, comma 8, comma 12. So can someone help me with this number? What is the LCM of 4, 8, and 12? Are you able to calculate? Okay, Sadaf is typing.
It is 24.
Okay, so both of you said 24. That is correct. So now this is 24, right? So now let's say this is when your time is equal to 0. So you have these three axes, right? So this is your for task 1, let's say. This is for task 2 and now this is for task 3. So what is the priority order for these given the time periods? So the one with a lower time period gets the highest priority, right? So we have priority order 4, 8 and 12, which means task 1, 2 and then 3, right? And the what is the execution time? So the execution time for them is 1, 2 and 3 respectively. So let's say over here we have one task, okay? Then task 2 is 2. So this takes 2 units of um oh wait, before that we should actually get this done. So after every 4 seconds this task 1 will a new task will come, okay? And now this task 2 is for 8, okay? 8, 6 and then 24. And then for task 3 is 12, okay? So after this it will come again, right? So now let's construct these tasks. So task 1 is only 1 and after again over here it will come, right? Now um task 2 is of 2 units, okay? So let's say you start from 1 and then you have it goes until 3, right? Okay, and same for the other one. And now the last one is 3. So it will start at 3 and then it will end at 6. Same for this one. So you can construct some schedule that it such that this happens. Okay. So I think this is how it will work over here. So you can just see that which one is getting executed first and then just note them down in the order. How task 2 is divided. So it has a time period of 8. Task 2 has a time period of 8. So after every 8 units of time, a new task will appear, right? So this is how it is. So that's why I first created this window, like this is the time period for task 2. So I have put it just 1 unit after because the priority of task 2 can be after task 1, right? So the execution of task 2 will start after task 1 in the same time period, right? So that's why this is 2 units and 2 units of computation time. So this is basically the same time scale. If you merge these three together, that's how the tasks are going to be scheduled one after the other. Is that clear?
Yes.
You have a doubt in question 1. Does all the options provided are right in week 3 assignment? That we'll check later once we discuss that particular question. So if this is clear, we'll move on to the next one. Okay, so let's see what the next question says. It says construct the schedule according to the RM policy for the following set of periodic tasks: tau 1, comma tau 2. Okay, so here CI and TI are the execution time and period of task respectively. Okay, so again the similar thing. So you can just check if you draw that particular axis and then you divide them. So first of all, you have to calculate the hyper period. Since there are only two tasks over there and those two don't have any common factor, it will be 35, right? And then after that, you have to draw that scale, like the time scale, and then based on that, you can just schedule those two. All right. So I hope this question you will be able to do depending on the previous task, because it is the same question, just the tasks and configurations are a little different. Should I move on to the next question?
Yes.
Okay. Schedule sequentially. Yeah, so you can draw the a similar figure like this and you can figure out how the schedule is going to be. It can change to from task 1 to task 3. You are asking for which question? Question number 7 or 8?
Ma'am, as in general, like it will go from task 1 to task 2, then task 3, or it can change to direct from task 2 to direct task 3. That what I was asking.
It can do anything, given that the priority order is not being violated if you have all the tasks in, like, available at some point in time. Okay, so for example, over here when I schedule T1, after that I schedule T3 because there is no T2, right? There is still time available. So that can happen. Okay. All right, so let's move to the next question. Question says construct the EDF schedule for the following task set 1, 2, and 3. So here CI, DI, and TI are the execution time, relative deadline, and periods of task respectively. So yeah, so what is the question? It says EDF schedulable. So you will have to check the, so the priority now becomes the deadline. Okay, so this is your priority order now. So given this priority order, you have tau 2 priority greater than tau 1 and then tau 3. Okay, and what is your hyper period? It is your LCM of 6, 8, and then 12. So what is it going to be? It's again, I think 24, right? Okay. So given this and given this information already, you now need to construct that diagram again for this kind of configuration. Okay, so you can just have that and I think it should be okay. It is the same question, just that the priority order, you need to work on that. Okay, let's go to the next question then. So this is the one where this precedence graph was being asked for. So consider these 7 tasks. Okay, A, B, C, D, E, F, and G. We have this with precedence relations among them as A to C, B to C, B to D, C to E, and all of this. Okay, so the relations are given. And this relation actually implies that Y can start its execution only after the completion of X execution. So this G can only start its execution after D has finished. F can start only after C and D both have finished. Okay, so that's the condition over here. Now let's see, this says that assume that all tasks have arrived at t is equal to 0. Okay, they all have deadlines d is equal to 25 and their computation times are this. So you have to modify their deadlines similar to EDF star. This is what we just went through. And then consider the new release time of a task. Consider that the new release time of a task can be replaced by the maximum between the finishing time of its immediate predecessor and the release time of that task. So with these, all of that, assume, I mean, you need to construct the EDF schedule. So assume that the period of each task is the same at its as its deadline. So now for this question, let's construct a table again. So I'll be using this space. So you have different tasks A, B, C, D, E, F, and G, right? And then you have their exact time. Okay, there is this original release time, then you have, let's say, a modified release time which we will calculate, then you have the original deadline, and then you have your modified deadline. Okay, so what is the execution time given? 2 3 3 5 1 2 and 5. So it is 2 3 3 5 1 2 and then 5. Okay, so original release is 0 0 0 0 0 0 and 0, right? And what is your original deadline? It is 25 for all of that, right? So 25 25 25, right? Now let's start changing their deadlines. So how are you going to check? What are the leaf nodes? Can someone tell me what are the leaf nodes in this graph?
A, E, and G.
How do you say A, B, and G?
A, E, E for echo and G for golf.
Okay, why would you say that?
Leaf is the ma'am the last node, na?
Correct. So do you see something wrong over here in this A, E, and G?
Leaf node is only A, and then
What is the definition of leaf node? Can you tell me again?
leaf node. What I know is okay, which is at the last of the tree.
Correct.
So
Endpoints, right? Let's say. So over here, how does the graph go? Like, what is the starting point of the graph?
start point is A only.
Okay, so if start point is A, how can end point be A?
No, end point
Start
is G, ma'am.
A
G.
and B both, right? Because they
So
both
end
don't
point is
have a predecessor. So what is your leaf node? Leaf node means they don't have any downstream, correct? So can you tell me?
A, ma'am. A.
How can A be a leaf node when you already told A is the start node and you're saying that leaf node is an endpoint? Think through and then tell me the answer.
Endpoint is G. Endpoint is G only.
Okay, are there any other endpoints other than G?
So endpoint is F, F and E also, ma'am.
Okay, why do you say that?
Because after E, there is nothing, ma'am, to go. So,
Okay,
so that is why E is the endpoint. Similarly, after F, there is no path to go. So that is the last point. Similarly, G also is the last point. No, you cannot go beyond that.
all right. Okay, so since those three are your leaf nodes, and what did we discuss over here? That for your leaf nodes, we do not change the deadlines, right? So the modified deadline for these three are still going to be 25, 25, and 25, right? Now, let's see for D, okay? So D is actually dependent on F and G, right? So, and what is the deadline for D? It is 25. So we have to take minimum of 25, comma, minimum of F and G, right? So for F, the deadline minus the compute time is this. And for G, deadline is 25 and compute time is 5. So you take this, right? So it is minimum of 25, comma, this is 23 and this is 20. So the minimum from these two is going to be 20. So finally it is going to be 20. So that's how you calculate the deadline for D as 20, right? And similarly you will finish the rest of them. And then after that you are going to calculate the um, release time also, depending on whatever their schedule is, right? Because now you have this earliest deadline for schedule, so you have to construct that schedule. So once you have the deadlines for all of these, you can just start constructing the schedule. So will you be able to fill up the rest of them? Because I already did it for 4, they were straightforward, but you can calculate for A, B, and C, and then construct the schedule for your um, yeah, this EDF. So is this question fine?
Can we go for C also, ma'am? One more, then it will be very clear. Or we, or we will try.
All right. So this is okay. So we have covered 4 questions. Um, Now let's see. Yeah, before going to these, there is another chunk of theory that we need to cover. So yeah, over here we have this response time analysis in a processor. So let's say given a task set Ti, each task is represented by your time period, deadline, and then your execution time. Correct? So each task has a fixed unique priority, which is this DM or RT or any other scheme, right? So now again, all tasks are preemptive, all these things are there, this is fine. So this response time is denoted by Ri, and for each of these tasks in any scheduling algorithm, we need to compute the response time. And we need to compute the response time such that this is the condition, that response time is less than equal to deadline. Okay, so now let's say if you have a fixed priority preemptive scheduling, how do you calculate the response time? It is EI, which is the execution time of its own task, plus this is actually summation over all the J's, such that the HP is the set of tasks of higher priority than Ti. Okay, so basically over here the idea is that your response time is going to be equal to the execution time of yourself plus the execution of the task who have been executed before you, right? And what tasks will be executed before you? The tasks which have a higher priority than you, right? So that's what is this term saying. So the above response time, you calculate it recurrently like below. So you have this Ri of n plus 1 as this execution time, and then you have Ri at n plus Pj and then Ej. So this n is, I think, your the time period when you are going to calculate, and the initial condition is 0 and the terminal condition is this, right? So if for any time period this doesn't change, this is equal to this, then we don't calculate after that. Okay, so yeah, so over here one example is given. So let's say you have this kind of a data where you have these different kinds of tasks, and time period is different again. Deadlines are there, execution time. This type you can ignore for now because this is more like to make you understand what is there. And then you have the priority. All right, so the response time for task 1, okay, so R1 0 is equal to 0. That's what is given over here also. Initial condition is like that. Okay, so R1 of 1 is equal to E1 plus R1 0 plus P2 into E2, right? So E1 is how much? 5, right? So we have 5 plus, it should be R1 of 0 plus P2 into E2. So since this is 0, this is equal to be going to be equal to 5, right? And then this R1 of 2 is equal to E1 plus this. So now over here we have E1 is equal to 5. So 5 plus R1 of 1 is again equal to 5, right? So this is equal to 5 divided by P2 is how much? So what was your P2? So this is equal to, this is for all the set of tasks that have a higher priority than your task, right? So over here, this is the task that is having a higher priority. So this is going to be equal to 8, right? No, the time period is actually 20. So it is going to be 5 by 20 into what is E2. So E2 is equal to 8, right? Something is off. So R1 of 1 is 5. So E1 is also 5. And the only task that is having a higher priority than you is for 20, correct? J belongs to that. And Ej into Ej. So that is equal to 8 only. Hmm. I think there is something wrong with the math over here. But it should be this, right? Because R1 of 1 is equal to 5 for you. And your P2 is equal to 20. Okay, and your E2 is also equal to 8. So this is 2. So you have 7, right? And then when your R1 3 is equal to how much? It is going to be E1 again, which is 5, plus R1 of 2, which is 7, divided by P2. What is my P2? P2 is again my 20 into E2 is equal to 8. So that is going to be a little different. So I think this calculation is a bit wrong over here, unless somebody else is understanding what's going wrong with the math over here. Okay, so this is one kind of a problem which you have in your assignments. Okay, um, And similarly, you calculate the response time for the other tasks also, right? And for T3, I think it was given over here like this. So now the question is that we calculated the response time, but we also need to check if the response time is not violating your deadline. So the response time is 38 and your D3 is 30. So the deadline is not met for the control task, right? So if we increase the period and the deadline of the control task to 50 milliseconds, then it will meet the deadline. So somehow you need to see that your deadline is actually tuned a little bit so that your response time is within the deadline. Okay. Mm. Yeah, and we also have to make sure that the utilization is less than the that number, that is n into 2 to the power 1 by n minus 1. Okay, so that is the thing. I think let's go back to the questions that are involving this kind of a theory. Okay, I think before going to the question, I think one more theory is required because these questions they need busy period and the blocking time as well, because the response time question is like later. So let's go through that also. So now this section is for bus level scheduling. Okay, so if you have a bus, so the communication between these various compute units is established by exchanging messages over the communication bus. So multiple messages are exchanged over the bus, right? And there are different protocols by which you can do the communication. It is time triggered protocol. So this is time division multiple access. Then you have the CAN, which is event driven, and then you have a hybrid. So I think in this session they have only focused on TDMA and CAN. All right. Yeah. So in the earlier slides, it was only showing until here, right? And now we have this extra part where we have this actuation. As I said, that actuation will also come later sometime. So we have this sensing task, then this is your control, this is your transmission, this is what you have received from the bus, right? And then this is what your actuation task is. All right. So now over here, you have this TDMA, right? So over here, this time division multiplex access is where the messages are transmitted in a predefined time window, which is called as slots. So a TDMA communication is characterized by this cycle length T and the slot length S. Okay, so this is your slot length and this is your cycle length. Okay, so the slot length can be different for different slots. All right. So here the relation between this slot length and the cycle length is given by this equation. And if your slot length is equal and there are n number of slots in the TDMA cycle, this is the thing. And if a message MI is scheduled to this particular slot, let's say SI, then the start time and the finish time of the message transmission is given by this. So what is this? This is TF is equal to TS plus SI. So final time or the end time basically is equal to start time plus your slot length. Okay. So now the question comes about calculating a buffer time, right? Let's see where that is. Okay, that comes in the CAN bus level, I guess. Yeah. So this is where we will focus our attention to. So in the case of CAN messages, we calculate this response time analysis. So your response time of a message is given by WM plus CI. And what is your WM? That is the queuing delay. As I said, right? It has to stay in the queue before the until the point where all the tasks which are ahead in the queue, which means the tasks which have a higher priority than your task, is going to get executed. So this is the longest time before a message gets access to the bus. So that is the queuing delay, and this is your compute time. So the queuing delay is composed of this blocking time due to lower priority, which may be in the process of being transmitted when message MI is queued. Okay, so your blocking time for a message is the maximum of compute time of all the messages which have a lower priority than MI. So now let's see. So the blocking time, let's say this is some kind of a scenario where you have three messages with three different types of periods. Then you have these deadlines and all of this, and then identifier is also given. So now, since they don't say if it's EDF or something else, then you take identifier as your priority order. So the lower the identifier, the higher is the priority, right? So over here, what do? We have B of M1 as 12 milliseconds. And how did they calculate this? So B of M1, so which message has a priority lower than M1? Can you tell me? No, actually, this is greater. So what should go in over here?
And the message which has lowest time period should be more prior.
And that's what is already given, right? The identifier is also in the same order. Actually, an identifier is given. So earlier we had like
So, ma'am,
red,
if we
right?
see
That.
the identifier, if
Mhm.
we see, then message one is the first priority. Sorry, message
How?
two is the first priority. Message one is the second priority, and then message three is the third priority as per the identifier.
Correct.
However, if you see the time period, so that with the time period frequency is opposite of
It's the
time
same
period.
order, right? No, it's the
Yes.
same order. It is still M2, M1, and then M3, right? Based on your time period also. So priority of M1 is greater than M3 over here. And what is the compute time of your? So you have to take the maximum of compute time of all the messages that are lower your priority. And since it's only 12, so it is 12. If you want to take for BM2, both M1 and M3 are lesser in priority. But what is the maximum compute time for both of these? It is 12. So the blocking time for this is also 12. If you want to calculate for M3, since it has a lower priority and there is nothing which is after this, so the blocking time for that particular message is equal to 0. Okay, so I hope this calculation of blocking time is um, easier. Now let's calculate this busy period. So there is something called as this busy period of a message, and that is the time duration starting from the critical instant till all the released instances are successfully transmitted. Okay, so let's see this question. Yeah. So you calculate a busy period for a message MI with priority such that this equation holds. So this P of Mi and k plus 1 is equal to B of Mi plus, and then you sum over this entire thing. So this T of Mi and k, so this is like from the previous round as we calculated earlier also, and divided by this PMJ. Okay, so PMJ is actually the time period for all the messages which have a priority of Mi or higher. Okay, so you include Mi as well on over there, and then you multiply it with the compute time of that. So you initialize actually as t is equal to that compute time of the message, and then you terminate on this condition. So the convergence is guaranteed as long as you get the utilization which has this value. All right. So over here they have done a busy period computation. So if you have these three messages, so how do you start? Let's say for if you want to calculate for M1. So initially, how do you initialize your busy period? You initialize using this compute time. Um, okay, you didn't calculate that before. Okay. So let's say you initialize this t is equal to cm1. So your t is equal to cm1 is equal to 5. This is fine. Okay, bm1 is already calculated from this because it's the same table, right? So your t of 1 of m1 is 12 plus, what do we have? 12 is your busy period plus the time in the previous step, which is 5, comes over here, divided by PMJ, the priority of M1 or higher. So the priority um, of M1 is 2. Let's put this. So it is M2, then M1, and then M3. Okay. So HP is the set of messages with a priority of M1 or higher. So it is taking M1 first, okay, which is 5 by 30 into 5. Okay, this is what it says, right? 5 by 30 into 5 plus, since M2 is also present, which has a priority of M1 or higher, you take 5, which is this part, divided by 20 because of M2 into 8 because its compute time is 8, and then you calculate 25. Okay. Now T2 of M1 is again the busy period remains the same always. But over here now you replace this value with the one that you got in the previous step. So 25 comes here as well as here in the numerator. The denominator remains like whatever message you choose depending on the priority, and then you calculate. Now if you see 33 comes over here and the rest of the values remain same. And then 38 goes here and here. So since 38 is common again over here, you stop the iterations, and then you get this busy period equal to 38 for M1. Okay, and similarly you calculate for M2. So M2 we got this busy period at 12 earlier. So you calculate this T of 0 of M2 is 8. Why? Because the compute time is 8. And then you have T1 of M2 is 12 plus 8 by 20 into 8. Why? Because M2 there is nothing higher than that. So you just take into account 8 and 20. Okay, and then similarly this. Okay, and then you calculate for message 3 as well. Alright, and once you have your busy period, right, which is this TMI, and if it is less than that, which means that one instance the message arrives within the busy period, the response time is the same as the busy period. But if this arrives, I mean, which means that multiple instances of message arrive within the busy period, then the number of such messages arriving would be this much. All right, so this is how you calculate that. um, Response time, I'll just solve one example and let you know, and then you can continue. So was the calculation of busy period and busy time, sorry, this is busy period, and then there was what, blocking times. So are these two clear, blocking times and busy period?
Yes.
Okay, so let's see if we can solve some of the questions. Yeah, so the first question over here says compute the blocking time of each of the message. So you know what you have to do, right? So for the first one, you first arrange them in this priority order. So what do you have over here? You have M3, then M1, and then M2, right? Now what do? You have to calculate this. Blocking time is the maximum of the compute time which have priority lesser than you, right? So for one of them, I'll do it. So for, let's say, blocking of M1. So it is the M2 which is lower than U. And what is the compute time of M2? It is 12. Okay. So that will be the thing. So you can similarly calculate for the rest also. For just a second. So B of M1, okay, sorry. So B of M1 is actually going to be the compute time of a message which has a priority lower than you, right? So you have to take the compute time of M2, which is going to be 8. Okay, and accordingly you can calculate for the rest of them. So this question should be doable. Now let's see. It says considering the same CAN bus setup in the earlier question, you have to compute the busy period of each of the messages. So you already have the blocking times, right? So you need to calculate the busy period based on these. Okay. So just keep in mind that over here in this question and in the question given over here, these parts are same. The identifiers are different. So make sure not to just replicate the answer, but solve it through depending on what is the priority order, and you should be able to get it. Okay, so I think this also you should be able to calculate. Now, considering the CAN bus setup in question 1, compute the response time of each of the messages. Okay. So the next question is about the response time. Yeah, this is a bit tricky, but let's see. Again, it's the very same question like this. Okay. Mm, okay, response time starts where? Okay, it starts over here. So first you have to calculate if the time period and if the um, if the busy period and the time period they are less than or they are greater than this condition, you check first, and then you calculate this number of messages that are arriving within your busy period. Okay, and if that is happening, then you kind of get this response time analysis should compute the response time of all the QMI instances. Okay, and the response time for the first instance will be 0, and then it will just go on, and the worst case is going to be the longest among them all. Okay, so now let's see if there are two messages at this time. So you have this 12, and Then you have this message 2 coming over here, and then message 1. The I think it's the second iteration, right? So the message 1 comes now, and then you have this as the response time of message 1, and your busy period is 38. So over here you have two M1 which are coming in M10 and M11 within the busy period 38 millisecond, right? Because busy period, and what is the time period? Time period is your 30, and this is given over here itself in this table, right? For M1 your time period is 30, so definitely that is greater, and then you have 2. Okay, so you have to get the response time of those two messages. So the first one, it is going to be 33, and for the second one it is going to be 8, right? So that's how you got for RM10 and RM11. Now RM1 is actually just equal to max of these two, which is 33 millisecond. So how do you compute for each of them, like when q varies from 0 to whatever it is? Okay, so then you do all these computations. So have you gone through the lecture in general? Because if I'm gonna repeat these, this is just going to be there in the lecture as well. Could you raise your hand? How many of you have gone through the lectures? Okay, Anupam has gone already. So is this theory that I'm trying to go through, it's already covered in the lecture, right?
Yes.
Okay, great. So I think if you refer just the lecture and then try to solve the problem, it should be doable because the question is the same. It's just that the priority order is different a little bit, and they have solved it beautifully. So I think you can do it too. And they have done it for RM1 totally, and RM2 and RM3 you should be able to do in the same manner. Okay, I understand this assignment is a bit lengthy, but the correct materials are there in the lecture, so it should be fine. Okay, so response time you should be able to calculate using the same theory. So now this is the last bit that we are left with. Okay, let's see if we can do this because theory is no more there. This is just the end of it. Alright, so this question says that a real-time operating system runs in PUA that follows deadline monotonic scheduling. Alright, so unlike this earliest deadline first scheduling policy, DM is a fixed priority static scheduling policy that gives highest priority to the task that has the smallest deadline. Okay. And in each sampling period, the task TS sensor control and transmission are released respectively at 0, 1.8, and 9.5. Alright, so following are the details of the tasks that are mapped in PUA. So these are the tasks that are there. Okay, so understand that this PUA is more like your compute units. Okay, so you have this sensing over there, then you had your control task, and then you have your transmission task, right? And period is the same for all, and then you have this relative deadline, and then you have this WCET. All right, so at t is equal to 0 you have only sensing task, correct? And then at t is equal to, so this sensing task executes from 0 to 0.2, right, millisecond. Now your control task is released at t is equal to 1.8 millisecond. So your TC, I'll write TS over here. This is from t is equal to 1.8 millisecond. up to how much? What is the, this is 3.2, right? So 1.8 to 1.8 plus 3.2, that is equal to 5 milliseconds, correct? And now your transmission task is available at t is equal to what? 9.5 milliseconds. Okay, so you have 9.5 plus how much? 0.5 is equal to 10 milliseconds. All right. So the control task is available to be transmitted only at t is equal to 10 milliseconds, correct? So now what next? Okay, so we have analyzed the first part of the problem. Now the question says consider the communication bus follows a time division multiple axis. So this is TDMA scheduling policy with a bandwidth of 12.8 kbps. So if your bandwidth is 12.8 kbps, so and if you want to transmit 8 bytes of data, how much does it take? 8 into 1 by 12800, 12,000, right? This is 5 milliseconds. Okay. So for 8 byte data, it takes 5 millisecond. Okay. So that is the next part is the transmission task transmits the 8 byte control data in a particular slot in every cycle of TDMA. So every transmission task transmits this much control data in one slot in every cycle of TDMA, which means it takes 5 millisecond of that slot. So every slot is how much? It is of 5 millisecond, let's say. So now the question is, consider another processing unit PUB connected to the bus. It receives the control data by executing the recipient task and then the actuation task. Okay, so do you remember this thing? You had one sensing task and then you had one control task. We had the TTX that goes to the bus. Okay, if this is your bus, and from this bus, the other compute unit picks up, which is your TRX, and then you have TA, right? So this is the thing that is happening over here. And the real-time operating system that runs in PUB follows earliest deadline first scheduling policy. So over here you have this EDF. Let's say this is your PUB and this entire part is your PUA. Following are the details of tasks that are mapped in the PUB. Okay, so this is your PUB and you have to calculate the offsets. All right. So basically, mm, two of the offsets of TA and TRX, and then later you have to calculate the minimum sensor to actuator delay in milliseconds. Okay, so let's see how you will solve this. So what is the periodicity of your control task? It is 25, right? So your TDMA cycle length is 25 millisecond, but the slot size is how much? It should be at least 5 millisecond because you are sending your 8 byte of control data, right? And your control data is available only at every 10 milliseconds, right? So if you have this, let's say your cycle length is 25 milliseconds. Maybe I'll draw it in the other side. This is, let's say, your cycle length. Okay, TDMA cycle length. This is how much? 25 milliseconds. Okay, and every slot is equal to how much? This is 5 milliseconds, right? Because you are sending 8 byte of data, right? And but your control data is available at every 10 milliseconds in the bus. So let's say your first control data was available then, and then after 10, and then after this, right? So now what will happen? So you are allocating it to every third slot in a TDMA cycle, right? So this PUB, which is your second one, it's actually receiving it at every 15 milliseconds, right? Because, oh wait, it should be third, right? 1 second. So once you fill in this part, and over here you have this slot cycle. Okay, and your PUB receives at every 15 millisecond. So, okay, let me get the diagram from there. Mhm. Yeah, I think it is from here. Yeah, so this is the thing. So this we went through, right? So we have this entire cycle length. So right now this is what is our cycle length? That is 25 milliseconds for us. Okay. And then our slot length is how much? It is 5 milliseconds, right? And since your control data is available at every 10 milliseconds, so let's say initially 5 plus 5 is your 10. So you give it to every third one, right? Um, so what do you have to calculate? We have to calculate the minimum offset of TRX in milliseconds. So have they mentioned the word offset anywhere so that I can point you? Okay, there is actually one example over here. So it says if your cycle length is, let's say, 4 millisecond, fine. So 0 until 4, right? And it takes 0.5 millisecond slot to transfer something. So this is your TDMA cycle. So every 0.5, you have this. All right. So 8 slot is like this. So for us, it should be 0 until the end of, and from here 25. This is 25, right? Hmm. So now, okay, you have to calculate the offsets. And again, in the same question also, you have EDF scheduled in CU2. So you have to find out the minimum offset. How do you do that? Hmm. Let's say CU1, the minimum total delay to execute TA is TS, TC, bus, and then TA, ignoring the communication task, is this much. All right, let's see. If your TDMA is this much, and then your bus is over here, it is picking up the transmitted values. Hmm. This is not. Okay, I think you may have to draw something like this. Okay, let me copy paste and put this over there. Okay, I'll put it a little above. All right, so let's revisit this problem. It is similar, it's just that it takes a little time. That's okay. So now over here, this is your TC, which is 5 millisecond. Your TS is zero point 0.2 milliseconds. But I think over here there are some delays. Okay, so you may have to check that part a little bit.
This WCTS should also be taken somewhere, man.
Yeah, we have already taken this right over here while calculating. So at the time, whenever something was being available, we were adding this WCET over there, right? 0 plus 0 0.2 for the sensor, 1.8 plus 3.2 for the TC, like the control data, and 9.5 plus 0 0.5 for this TX. So basically, we have the control data available at 10 milliseconds. So over here, right at the end of 10 milliseconds, in the third slot, you are going to have your data available, right? So when will your other, like, so this is the part. So let's say if you have this as your bus, right? I was trying to relate to that figure, but I'm not able to. 1, 2, 3, 4, 5. Let's say we have that, right? So your control data is available until this second slot, right? So it will be available in the third slot to be taken by the second bus, right? So you can calculate what is the offset of reception at this other one. That's when this slot ends actually. That should be your offset for the TRX actually. Okay, that would be that. And I think for TA, which is for actuation, that would be right after that. So let's see what is the WCET for that. So it should be actually TRX plus WCET. Okay. But over here it is having this EDF scheduling policy. So you have something called as a TSEC also. What is TSEC? Has it been explained in the question? No. All right, no issues. But either ways, the one that has a lower time period gets a higher priority, correct? But over here they should have actually at least given the deadline because it is supposed to be earliest deadline first scheduling policy. And if you don't give the deadline, we cannot like check the exact one. So even if there is no offset, I don't know how to relate that exactly. But let's see. So if this has the lowest one and then you are receiving this TRX at the same time, so this one gets executed first, okay? And your TRX is going to execute right after that. And then your TA will get executed because this is supposed to be the pipeline. So TA is anyways going to be executed after TRX, right? So you can calculate the offset of this TA based on this TRX, okay? Yeah. So since you have this TSEC getting completed before TRX, right? So you should add the time of this TSEC Okay, at the time when you are receiving this TRX, but at the same time this new task is being created and is being executed. So you need to check that what is going to be the offset for that, and then plus the execution time of TRX should be the offset for this. So it should actually be TRX, the time at which you are going to receive it, plus tsec is going to be your offset for TRX, offset of TRX, and this plus WCT of your TRX is going to be your offset for the next one, right? TA. So that's how this entire problem should happen. So I've told you a very simplified version of it. You can still go back and go through this example, which may help you clear properly, but this is how practically it should work. Okay. Yeah, and the last bit is simply um, just to calculate the response time, which is sensor to actuator delay in milliseconds, which is your response time, right? So you have to then calculate that the time at which your TA is starting, which is your offset, plus the total time for your actuation to happen. Okay, so that is would be your end-to-end time. All right, I think by using these things, you should be able to solve this question. Did I miss anything else? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think all the questions are covered. Let me know if you need some more help in this or any other question in general.
So what is in this, ma'am? TRX and TA and TSEC?
So TRX is actually the task that is responsible for receiving your message, right? We checked over here in this
Value,
example. Sorry?
value what value what we have calculated, ma'am, and we have not proceeded at that. The values.
No, if I calculate, that would be the answer. That's why I did not proceed. I just told you the method, how you can get it. So I calculated up to like 80% of the question, and the rest 20% you have to get using these equations that I have written over here.
This is not visible. TRX plus TSEC is equal to TRX. What is that? Please thoda elaborate.
No,
Zoom out, ma'am.
it is actually, so you have your transmission data available at 10 milliseconds, right? So your transmission data is available only in the third slot because your slots are only 5 milliseconds in length, right? So in the bus, your data is in the third slot. So your second PU is going to pick your data from the third slot, right? But then, since this is earliest deadline first, and they haven't given the deadline as such, so I took this period in millisecond as the deadline, let's say. So your tsec will be executed before, and then your trx would be executed. Okay, so tsec, the execution time of tsec is how much? It's 1, right? So you have to wait for 1 millisecond before you can execute your trx, right? And since you are getting your this trx after this tsec, and your ttx is available only at the end of this 15 milliseconds, so you can calculate according to that. And after that, so after that tsec will be there with this execution time, then you will have trx with this execution time, and then you will have ta with this much execution time. Okay, so that is how the progression goes. And then you can calculate the offset for this, offset meaning that till what point you have to wait that your trx should start. Then ta is like at what point you have to wait till your actuation task can start, and your end to end time is like this offset plus your wcet of your actuation. All right.
Okay, ma'am.
Okay. All right. So if anybody else has any other question, please feel free to ask. We can officially close today's session. Thanks a lot for joining, and we'll meet next week on Saturday again. Thank you.
Thank you, ma'am.